Back, students. Today we're going to continue talking about limits. Specifically, we will start with continuity and intermediate value theorem. Okay, so in the previous lesson, we learned, we noticed that we need continuity, right? When we can directly evaluate the limit at the point, right? So essentially, the polynomials are continuous, right? And continuity defined as a function f is continuous at the number a if this equality holds, right? So the limit of f of x as x approaches a is equal to the value, right? To the value of a function at that point, right? So remember, this is how we would look at it graphically, right? This is a continuous function, right? Because we don't have any jumps, right? Meanwhile, a function like this would not be continuous, right? Why? Because if we can have a limit, right? We can have a limit here. So this one is not continuous. Even though the limit exists and the function value exists, right? Why? Because, well, if we go from the left, it's going to be this value. If we go from the right, it's also this value. But if we evaluate f of a function, it's going to be all the way up here. So this two will not be equal, even though both of them exist and well defined, right? But the function is not going to be considered continuous. Right? So we always have to double check every time we work on something. So a few more examples. Take a look at. So which of the following functions are continuous? And so let's take a look. So here's 4 examples. Right, so a is actually continuous, and we have it's continuous. Well, it has the value, right? It has the limit value. Okay, right? But f of 2 is not defined, so f is discontinuous, right? So here the limit, right? So even though f of 0 is equal to 1 is defined, but the limit, it does not exist, right? It approaches infinity, so the values are not. Meanwhile, this one, even though this one, both of the so the limit exists, the value function exists, but since they're not equal, then the entire continuity, right? So same thing here. This function is not continuous. Okay, so there are plenty examples of functions, right? But the continuous ones are like polynomials, right? Polynomials, or sine function, cosine function. So most of the functions we know are continuous, right? If not all of them, right? But of course, there are special examples, and those examples are not as easy to construct, right? Like for example, this one is easy to construct, right? This one is actually rational. Deal with rational functions a lot, right? And we know that sometimes they are not continuous, right? And we are not continuous at this specific point. Okay, so we can also have a definition that a function is continuous from the right at the number a if the right limit, right? If from the right limit we have it. Same thing, f continues from the left if from the left side. Okay, so let's give one more definition. So continuous on the interval, right? Because here we are doing continuity at the point, but sometimes the point is not enough for us. We want to make sure that we are continuous on the interval. So a function f is continuous on an interval if it is continuous at every number in the interval. So if f is defined only on one side of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Okay. So sometimes we have to watch out of what kind of continuity we are talking about, right? And here, an example, right? An example would be the following. So so we want to show that f of x, which would be equal to 1 minus square root of 1 minus x squared, is continuous on the interval -1 to 1. Right, so what are we going to do? We're going to go ahead and take the limit, right? So a limit of x approaches a, right, where a should be the interval. Okay, and that will be equal to limit as x approaches a of 1 minus square root of 1 equal to, so 1 minus limit of x approaches square root of 1 squared. So we could review previous lesson we did the loss. Do a loss. That will be equal to essentially 1 minus square root limit. Because square root is a power 1/2, 1 minus squared. And that's going to be equal to 1 minus square root of 1 minus a squared, which is equal to, perfect. So we just reached the definition of continuity, right? So that's it. We're done. We proved, right, that the function is continuous. Okay, now, well, what if we have multiple functions, right? Can we have a continuity at multiple? Well, we can have a theorem on that. So a theorem, so if f and g are continuous at a and c is a constant, then the following functions are also continuous, right? The combination of f plus g, the subtraction of f minus, the constant multiplication, c times 0. And, well, because c of 0 would be not interesting. So for f times g, also continuous, this is very interesting. F over g is also continuous as long as f of g of a is not, right? Because we might be continuous, right, at the point, right? So point-wise continuity as well, we can be, but that means that maybe on interval we're not continuous, right? Because there will be a point at which we're not continuous. We can prove it. We can prove each one of them by using the limit laws, right? So for example, we're going to prove only one of them. So let's say, well, f plus g, right? So limit as x approaches of f of x plus g of x, right? That's going to be the same thing as limit x of f of x plus limit of x approaches g of x. And since both limits exist, right, because both of them are continuous, so they must exist, so it's going to be f of a plus g of a, right? And that's essentially the same thing as f plus g evaluated at a. Okay, so that is continuous. So we can do the same thing for the other ones by using the limit. Okay, now one more theorem that we can talk about. So, and that theorem is about the polynomial, because last lesson we talked about the polynomial, but we said anything much about besides of them being having that property. So, but now we can make a theorem, right? A theorem. So any polynomial is continuous everywhere. That is, it is continuous on the entire real number line. And so B, any rational function is continuous wherever it is defined. That is, it's continuous on its domain, right? That would make sense, right? We can be continuous on domain. So we can prove part A. So essentially, if we define any form of the polynomial, right, we know by the limit laws that we can apply limit law. By limit laws, everything's going to be 1, right? So part A is easy. And part B is also not too difficult because, again, of the limit law, right? If the fraction would be continuous, then we would be continuous everywhere, right? So beside of its domain. Okay. So for A, you can think about a polynomial in the form of Cn x to the n plus n minus 1, x to the n minus 1 plus, etc. Size of a polynomial, c1 x plus c0, right? We can apply limit of x approaches a of 0, and limit of x approaches a of x to the power m is equal to am. Right, this is the two laws that we know. So therefore, by that, p of x is continuous. And it's going to be specifically continuous everywhere if a is going to define as any number. Okay. Meanwhile, for part B is going to be, right, we're going to say that f of x is going to be p of x over q of x. Right, and then p of x and q of x, so we're going to say that q of x is 0, right? Doesn't have 0. So, but we're going to have a domain and they're both continuous. So then both of them are polynomials, right? And we know that P is continuous everywhere and Q is continuous than by the previous, so the theorem 4, right, which is this theorem, right? We will be able to say that this is going to be true, so therefore very continuous. Okay, and it's going to be continuous on the domain, wherever the restriction is. All right, perfect. Now, it's going to be a theorem, right, which we previously mentioned it, but let's write down all of the functions that are continuous at every number in their domain. Right, so wherever the domain is, the function is going to be continuous. And this is the majority of functions that we are going to be using in calculus. Right, so the following types of functions are continuous at every number in their domain. So polynomials, rational functions, root functions, metric functions, inverse trigonometric functions, exponential functions, big functions. Right, this is the majority of the functions that we are using. Right, as you can see, there becomes difficulty with piecewise functions, step functions, because it might be difficult for us to define the continuity. Okay. All right. So, and let's go ahead and take a look at one more theorem. So if f is b and the limit of g of x as x approaches a exists, which would be, then the limit of f of g of x, right? So composition of two functions is also true, right? So the composition of the functions, and this is it's reasonable because we can use our we can use the limit loss, right? And we can prove through the limit loss that this is going to be the case. Okay, perfect. And for example, we can use it for a function like this. So let's take a look at example. So let's say we're going to have a limit of x approaching 1 of arcsine, right? Arcsine is inverse of sine of 1 minus square root of x over 1 minus x, right? So essentially, this is a composition of functions, right? And we also had a composition of functions when we were working with x squared times sine times 1 over x, right? So, okay. So here, right, essentially what's going to happen is we're going to just bring in, so arcsine is outside, so the limit of x approaches 1 of the expression of 1 minus square root of x over 1 minus x. So this one we can simplify, right? So we're going to have arcsine and the limit of x approaching 1 minus square root of x divided by 1 minus square root of x, 1 plus square root of x. Okay, so that's equal to arcsine, and here this and this cancel out. So it's going to be arcsine of a limit as x approaching 1 over x. And if we evaluate, it's going to be arcsine of 1/2, which should be pi over 6, okay, or 30 degrees, right, in other words. Okay, so we can develop essentially a theorem on the composition functions, right? And the theorem that we're going to get is if f and g, or fg, so if g is continuous and f is continuous at g of a, then the composition of functions f of g given by f of g of x is continuous at point A. Okay, so, and essentially, we can say that since g is continuous, we have that limit exists, right? And then by theorem 8, right? So, since g is continuous, this is our little proof here, then limit of x approaching a x, then by theorem 8, we're going to get that limit as x approaches a of f g of x is equal to f of g. All right, perfect. We can also use it as our tool, right? As our tool to actually evaluate, right? Evaluate a composition of functions. All right, now let's go ahead and move on to the second part, which is going to be the intermediate value theorem. or in other words, IVT. One of the most important theorems of calculus. So essentially, it coming from continuity. Right? And let's go ahead and state it. So the intermediate value field. Suppose that f is continuous on the closed interval from a to b. Let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c such that, f of c is going to be equal to n. Right? So essentially, it guarantees that in that interval, if we have f of a and f of b, there is some sort of way function takes to reach that number n. And that means there exists an x value c such that we are able to reach that number n within that interval because n is between f of a and f of b. Right? So here we can have a very nice illustration. Right? So here it is. Here is two graphs. So right, we are in between. Right? So essentially in between f of a and f of b. Right? So this is our interval f, and there the value n is in between. Right? So that means there should be a way. Right? There should be a way of us being able to reach that value. There is no other way around. So, for example, right, just a classic example of just a regular function here. So, if the function is continuous, that means it has to cross all of the values in between f of a and f of b. Right? So if we have f of a and f of b, and the number n, which is the y value, is somewhere between them, there is got to be a way for a function to cross that value within that interval. So our c value is going to be right here, right? C value where f of c will be equal to n, and that's guaranteed by the continuity. Okay, so perfect. So essentially, what we will have to do, right? Let's take a look at an example, right? Why is it useful? Because if we know that we're crossing the x-axis, right? If we know that we're crossing the x-axis, that means we have to have a route to the solution. So, for example, right, we want to say that show that 4x cubed minus 6x squared plus 3x minus 2 equal to 0 has a root between 1 and 2, right? So x equals 1 and 2. So the first thing we gotta do is, well, we have to check, do we actually cross the x-axis between those two values? So f of 1 is going to be 4 minus 6 plus 3 minus 2, which is equal to negative. And that is going to be 0. And f of 2 is going to be, so plugging in, so we're going to have 32 minus 4 plus 6 minus 2, which is equal to 12, which is greater than 0. So yes, in somewhere, right, f of 1 is less than 0, less than f of 2. Right, so we're crossing the 0, right, when the function is 0. So we're actually crossing it there. Okay. So, of course we can go lower and lower, but essentially by the intermediate value theorem, it guarantees us that since the 0 is between f of 1 and f of 2, that means there got to be a way for us to cross it. So that means there is a route between f of 1 and 2. Right. Perfect. So next time we will do horizontal asymptote and a little bit more on the limits in general, and then we will be moving on to the new topic. Until next time.